things, okay, today, and we're going to be specific for each one. That's what we're going to get to today. All right? So just follow along here, and if you got any questions, I encourage you to ask, of course. We're going to talk a lot about molar enthalpy today. Molar enthalpy is always measured in kilojoules per mole. Okay? You'll see that, delta FH in your data booklet, kilojoules per mole. How much energy should we get from forming 1 mole of this? Or, vice versa, how much energy should we get from decomposing a mole of this, or something along that line? So we're going to focus on 1 mole of stuff here. All right? Delta CH, we've used that term before, combustion, the enthalpy change associated with the complete combustion of 1 mole of a fuel. Combustion is most often done as an open system, and we're going to get some, of course, gases that are allowed to escape, and some energy as well. In an open system, which basically just means, burning of combustion, propane's delta CH is a negative 2043.9 kilojoules per mole. So for every mole of propane that you burn, you would get 2043.9 kilojoules of energy produced. All right? Kilojoules per mole of that. You can represent this in different ways. A little bit of review for you. Maybe even for tomorrow. Who knows? Maybe we'll have a little quizzy quiz tomorrow. Yes? Tomorrow, I might ask you to do, once again, in 3 different ways. Delta H. So here's a balanced chemical equation. I'm telling you right now that this is balanced. Balanced chemical equation for propane, combustion of propane. And we said it was a negative 2043.9 kilojoules per mole of propane being burned. Okay? So in this case, I'm burning 1 mole, balanced chemical equation. I get 2043.9 kilojoules. You might want to write it in terms of a term within the equation. So you'd write it on the product side, right? So positive plus 2043.9 on the product side. And of course, last one, you might want to do it as a potential energy diagram, right? So exothermic, of course, products, balanced reactants, balanced products, delta H, negative 2043.9, okay? So all that stuff, if you notice, those 3 things that we did, we're really focused on the burning of propane, just propane, okay? So those all kind of related to that. What we're going to talk about now is how about, is there a kilojoules per mole for other stuff? Is there a kilojoules per mole for oxygen in that question? Is there one for CO2? Is there one for H2O? And the answer is yes. There is a molar enthalpy for each one of the reactants in each one of the products. Okay? The delta H for a reaction is always directly proportional, very important, okay, to the amount of substances that react. We know that. Okay? In fact, I don't even have to circle that because we've done that. Okay? So, for example, another example here. By the way, you should know this equation for the diploma and the Unit 1 test. Okay, so make sure where this is, again, photosynthesis. Okay, so that's the second time we've given you that. Make sure you know it. So, for photosynthesis to take place, we need 6 carbon dioxides, 6 waters, balanced chemical equation. We need 2,802.5 kilojoules of energy, and that will give us 1 mole of glucose and 6 oxygens. Okay? And that's the balanced chemical equation. I'm telling you, that's what it is. Now, if you guys know this, okay, this is not a big shocker to you. We've talked about this. Guess what? I produced 1 mole in that question of glucose. What if I wanted to make 2 moles of glucose? I want to make 2 instead. So right here, I want to make this 2. What do I have to do? Yeah, double everything, right? We got to double everything, right? So I'd have to use 12 and 12 and double, right? Which is what? 5605.0. Okay? Double and double, right? True? It's directly proportional, right? If I want to make twice as much glucose, I need twice the amount of energy, right? Makes sense? That's what directly proportional means. That's all we're going to do today, guys. Okay? So there's your balanced chemical equation for that, right? Directly proportional. Now, we're going to do something called, we're going to get back to that in a second here, but before we do that, we're going to look at this little formula here for us. delta H. So remember, delta H refers to the enthalpy change. This is the thing that you would find at the end of the equation, the delta H notation, or a term within the equation. This represents the entire equation, delta H, right? Look back here, delta H. 5605 is the delta H, the change for this particular reaction to take place, okay? This here represents for that particular equation, the entire equation to take place, we need that much energy. That's the delta H, the enthalpy change, right? Okay. This is always going to be measured in, by the way, kilojoules. Okay. And of course, you guys know that's the amount, right? Amount you have, and that's in moles. And delta RH is something we would call, we've seen delta RH before, we've seen delta CH, delta DH, delta FH, delta neutralization H, if you want, okay? This is the molar enthalpy, and that, of course, is measured in kilojoules per mole, okay? We've seen that before as well, right? So, you know, if we're thinking about this formula here, just think about this for a second. Look at that formula, right? I'll give you an example. Pretty straightforward, okay? Look, let's go back to this one here. No, let's go to this one. Actually, I'm going to go back to this one from yesterday here. So remember, in this question, if you go back to question number 3 from yesterday's homework, it said in the question, right, it said, the delta CH for this question here, it said, because it's a combustion reaction, it said that delta CH for benzene is a negative, what is it, 3135? Is that right? 0.5 kilojoules, I believe, per mole. Yes? Is that right? Somebody? So who's got question 3 from yesterday, real quick? Look at the actual wording of that question, number 3. Is it 31? 35.5. Yeah. Okay. So that's what it tells you in the question, right? We think about this. This is called the molar enthalpy. For every mole that I burn, I use that much energy, right? Well, look. Think about that. 3135.5. We used 2 moles. Yes. So what was the delta H? Well, twice as much. Yes. Twice as much, 6271. Does that compare to what we have here? Yeah. 2 moles, 3135.5 kilojoules per mole gives you the 62, whatever we had in that equation, yes? So it's just a fancy formula for basically the same thing that we've been doing, yes? Okay, so what we're going to do today, though, we're going to still do the same kind of thing here, but we're going to break it down. Not everyone's looking. Break it down. For each one by itself. Okay? So each one by itself. This is the balanced chemical equation for ammonia. I've given this to you. This is, you don't have to balance anything. This is it. One of the things that we don't talk about, this is once again your fuel here. So if you got nitrogen in the fuel, you get NO2 here. If you got hydrogen here, you get H2O there. Okay, that is the combustion of ammonia. Okay, that's what the balanced chemical equation is, and I've even given you the heat that's associated with this particular equation. So looking at this equation, if I took 4 moles of ammonia, I would need 7 moles of oxygen. It's balanced for you and everything. You get 4 moles of NO2, 6 moles of water, and you would get that much heat produced from that particular equation. Okay? If I wanted to figure out the molar enthalpy, okay, the molar enthalpy, then for each, let's just worry about each reactant. So basically, let me put it to you this way. Here's what we're going to do. I know, do you agree? Let's just focus on this right here. Don't worry about this or this or this. Let's just focus on this part right here. If I had 4 moles of ammonia, and yes, for a combustion reaction, let's say I have 4 moles. 4 moles gives me this much heat, correct? Yes? So what I'm asking you now is, well, what's the molar enthalpy? If 4 moles gives me that much, how much kilojoules do I get per mole? Yes? That's what molar enthalpy is, kilojoules per mole. How many kilojoules do I get for a mole if I just burned 1 mole of NH3? Right? Well, you can use a formula for this, whatever you want. In fact, I will start it with, I'm going to do NH3 here. But I'm going to start with the formula, and then I'll show you another way you can do this as well if you want. I don't care. What we have to understand here is that I want to figure out how many kilojoules per mole would I have here. What is the molar enthalpy of NH3? Well, let's see here. If you think about our equation here, it was delta H equals N delta. Now this is a combustion one, so you could do CH here. If you don't want to do that, if you want to just do RH, that's fine. Okay, but that's our equation. That's kind of the formula we've been using, right? And once again, I'll kind of show you a few different things. Well, if I want to figure out delta RH, right, do I not just take, in other words, the molar enthalpy, do I not just take delta H and divide it by N, right? Yes? So delta RH for ammonia here is delta H, which is a negative 1134.4 kilojoules. But remember, that is based on 4 moles of ammonia that's being burned. So divided by the number of moles, and I would get delta RH, which in this particular case, of course, dividing those two numbers, I think you get about a negative, somebody help me out, negative 283.6 kilojoules per mole. Okay, would be what we call the molar enthalpy. Molar refers to the term moles, right? The mole enthalpy of 1 mole of burning that, right? So look up here, once again. 4 moles gives me this much heat, right? What I'm saying to you is, what's the molar enthalpy? How much heat do I get for burning just 1 mole? That's what we call the molar enthalpy. So 1 mole here would give me a negative 283.6 kilojoules. Okay? And once again, does that mean that I have still 7 moles of oxygen and 4 and 6? No, you don't. You probably have, if we're going to divide this by 4, we need to divide this by 4, yes? And divide this by 4, and divide this by 4, and divide this by 4, yeah? But I don't care about the other ones. I'm solely looking for the molar enthalpy of this. I'm focused on that only, okay? So I don't care what the rest of the stuff is. I'm focused on that. That's the particular molar enthalpy of that reactant, okay? That's the important part here. We're focusing on one thing at a time here, okay? Now, do you have to do it this way? And the answer is no, okay? If you've taken my Chem 20 class, what's my favorite thing to do? I'll give you a hint. Huh? Say it. You know what I'm talking about. What's this? Huh? X-Man. No. Cross multiply and divide, right? Now, that's my favorite. I do that every time. I love cross. Racial proportion, eh? Oh, so good. Eh? You can do that too. I don't care. Look, hey, and you can do it however you want, right? If negative 1134.4 kilojoules is for 4 moles, if I want the molar enthalpy, I want it for 1 mole. Well, how much heat would you get for 1 mole? Yes? Cross multiply and divide. It's exactly the same thing, guys. You can do that and figure it out. You get the same number. Okay? That's all I'm doing. All we're doing here is grade 11 stoichiometry. except we're not figuring out the mass of the precipitate or the volume of the gas or anything else. This is grade 12, grade 11, grade 12. So we're looking at heat, yeah, thermochemical. 4 gives me this, so if I add 1, it gives me that. It's directly proportional, okay? And that is all we're doing today, all right? That's it. So just get that in your head, all right? Now, okay, I changed my mind. You know what? I don't care about the ammonia anymore. Now, I want to focus on, you might say this is silly, but what about this? What's the molar enthalpy of oxygen? Can I do that? Sure you can. You can do the molar enthalpy of whatever you want. Because if I use ammonia and I use 7 moles of oxygen in this equation, now I don't know what this is and I don't know what those are, but if I use 7 moles of oxygen in this particular equation, that gives me 1134.4 kilojoules of heat. Okay? So 7 moles of oxygen gives me 1134.4. How many moles, or how much heat would I get from burning using just 1 mole of oxygen? Let's say I reduced it, I can only use 1 mole of oxygen. How much heat should I get from that? Well, we can do that too. Let's see. Oxygen. Well, let's see. Delta RH is, of course, delta H divided by N. Negative 1134.4 kilojoules divided by the 7 moles of oxygen would give me, of course, I forgot now. Let's see, 1134.4 divided by 7, 162. And don't forget the negatives, of course, kilojoules per mole for the oxygen. That's my molar enthalpy of oxygen in this particular equation. Is it going to be the same for all the equations? Heck no. Okay, you're burning propane, it's going to be different, right? It depends on the balanced chemical equation. Yeah. Yeah, that's right. Because it doesn't matter, right? I know people get confused with this, but 4 moles gives me that. And I need 7 moles to go with that 4 to give me 4 and 6, and that's how much heat it is, right? So based on each one individually, I always get 1134.4, okay? For this particular reaction. Now, with a different one, it's going to be different, right? All we were figuring out is how much heat per mole for each one of these things individually, okay? And I'll show you why we're doing that in a second here. What about NO2? That's a product here. If we're looking for the delta RH, or the delta whatever you want to call it here, once again, we're going to take delta H over N, right? Negative 1134.4 kilojoules. But that is based on, for NO2, it's based on 4 moles again, right? 4 moles, when I produce 4 moles of product, when this is produced, I get also that. Well, what if I only produce 1 mole of NO2? Then how much do I get over there? Well, dividing it by 4 moles of NO2, I'll get out of your way here right away. Once again, you're going to get that same number, negative 283.6 kilojoules per mole of NO2. That's how much heat would be produced per mole of NO2. So I make, maybe perhaps in this particular equation, I can only make 1 mole of NO2. Well, I get 283.6 kilojoules. Okay? And once again here, we got 6 waters. So for the water part here, I'd say once again, negative 1134.4 kilojoules for 6 moles of water. And let's see. Oops. And I get about 189 kilojoules per mole, though, of water. Okay? And of course, each one's going to be a little bit different because you're producing different numbers of moles for each one of those, or reacting different numbers of moles. And if you have the same number of moles, of course, you're going to get the same molar enthalpy for those. Okay? So that's called molar enthalpy. What I've basically done here is changed 4 moles gives me that, yes. How much does 1 mole give me over there? 7 moles gives me that. How much does 1 mole give me over there? 4 moles gives me that. How much is 1? 6 moles gives me that. How much is 1 over there? Okay, so I've basically broken it down into each reactant and each product by itself. How much heat would I expect to get if I had 1 mole of NH3, or how much heat would I get produced if I made 1 mole of NO2 or 1 mole of water gas? Okay, and that's all you're doing there. That's called molar enthalpy. Okay, if you go back to this question here, you know, we look at this question, you might say, you know, how does this relate to what we did? We've done this before, right? Look, delta CH for benzene, right? I get 35.5 kilojoules per mole of benzene that I burn, right? That's the molar enthalpy for 1 mole. I had 2, so I doubled it, right? You might say, well, what about the oxygen? Well, you could figure that out now, but I didn't tell you that because I didn't care about that. I was focused on this yesterday, right? The one that I did tell you. Could you figure out the other stuff? Sure you can, but I don't care, okay? Could I figure out for this particular equation based on CO2 and H2O? Sure you can. I could figure out the molar enthalpy based on those. I don't care. I was given that, and I used that for my balanced chemical equation, okay? So, back to here, all right? That's how you're going to calculate molar enthalpy, okay? How are we going to use this? Yeah. How are we going to use this? Well, we're going to use, once again, a balanced chemical equation. So here we go, okay? Based on this reaction here, what's the enthalpy change? Well, when you see terms like this, if you want to use a formula, by all means, go ahead and do so. When it says, what's the enthalpy change, we're talking about delta H, right? What is the enthalpy change? Not the molar enthalpy. What's the enthalpy change when 2.18 moles of ammonia is burned? And you know me, I like to line stuff up, right? Yes? We did that in Chem 20, Unit 4. Stoichiometry. That's really what this is, right? We're lining stuff up, we're going to move stuff over, and we're going to figure out stuff, yes? Precipitates, volumes, in Chem 30, heats, all right? So, if I have 2.18 moles here, how much would I expect to get here? Well, honestly, the easiest way to do this is probably a ratio proportion, cross multiply and solve type of question. Sure, if you want to use the formula, that's fine too. To find delta H, you're going to take N times delta RH. Look, once again, do I care about oxygen or nitrogen dioxide or H2O for that matter in this question? No. I know that I have this for this, right? So I don't even know how much the other stuff I have. It doesn't say, right? The only thing I know is that. In fact, you could relate this to Chem 20 limiting reactant if you wanted to, right? This is going to determine this, right? So look, 4 moles gives me that again, right? So you might say, well, hey, how much does 1 mole give me? What's the molar enthalpy of NH3? Well, you would take your negative 1134.4 divided by 4, which we did on the other page, right? I'll just do that here. Divided by 4 moles, right? That would go there. Sorry, I should probably put just kilojoules there. That would go there, right? We did that on the other page. That's the molar enthalpy of NH3, delta RH, right? That's how we figured it out. Negative 1134 divided by 4, and you got a negative 283.6 kilojoules per mole from the other page that we just finished. How many moles? So you get basically what they're saying is you get 283.6 kilojoules for every 1 mole of NH3 that you burn. Well, it turns out I'm burning 2.18 moles. So we multiply those two together, of course, and we get 2.18 times negative 283.6, and we get 618. Negative 618, by the way, don't forget the negative, please. Negative 618 kilojoules is how much heat is going to be produced by burning 2.18 moles, okay? 3 significant digits, 2.18, so we should have 3 in the answer, yes? Okay, 618, 3. Once again, it doesn't matter how you want to do this, and I don't care, but you have to understand basically the ratio proportion. It's directly proportional, right? If you wanted to, could you say, you can set this up however you want. Like I said, probably the easiest thing to do on this, which you're really doing the same thing, guys. Negative 1134.4 kilojoules is for 4 moles of NH3, right? That is for 1134. If I had 2.18 moles, how much energy would you get out of that, or how much heat would you get, right? You'll get the same answer. Because if you look right here, what's this? Well, this is kilojoules per mole, right? That's how you find it. Times 2.18 moles, well, that's exactly what you just did there. And you find X, okay? And that'll be it. So 618 kilojoules of energy is released, exothermic, negative, okay? Make sure, all right? Now, how are we going to make this more difficult? Well, not really. I mean, we can make you do more work, that's for sure. Well, now we have 2.25 grams of nitrogen dioxide, which we are going to put here, of course, has been produced. So we did this experiment, and it turns out we got 25 grams. We measured out the nitrogen dioxide gas. We got 25 grams of it. What's the enthalpy change based on this? What is the delta H that's associated with this, therefore? How much did I actually produce? Yeah, we know, right? And once again, this is where sometimes people get confused. Hey, if I had 4 moles and 7 moles and 4 moles and 6 moles, I get that much. I know that, right? That's the balanced chemical equation. Eventually, you guys will figure out how to figure that out on your own. Hess's law. I know that 4 moles is going to give me that. I know that. The question, when I actually do this, though, are you going to get 4 moles in the lab? Who knows? You might get 25 grams produced. You might get 145 grams produced. It depends on how much you start with, obviously. It's all related to each other. So, in this case here, apparently I got 25 grams. Well, turns out I can find out the molar mass of NO2. NO2, 32, and that is what? 44.01, is that right? 32 and 14, no, 46, 46.01. My bad, sorry. Math without coffee in the morning is really difficult. Okay, and I can figure out how many moles actually was produced of NO2. Now, 4 would give me 1134. How much do I actually get? Well, it's not 4, it's actually closer to 0.5 here, a half. 0.5 something, 0.568 roughly moles was produced. Okay? Well, if I only have 0.568 moles produced, I'm certainly not going to get 1134.4 kilojoules of energy produced because I only made a half a mole, okay, of NO2, whereas 4 gives me that. Once again, you could do a ratio proportion kind of thing right now if you wanted to. If you want to be fancy and use a formula, by all means, that's nothing wrong with that either, right? So, what is the enthalpy change? What is that if I use 0.568 moles and the molar enthalpy, once again, I don't care about anything else. The only stuff I have here, guys, relates to NO2. So what's the molar enthalpy of NO2? Well, it turns out it's the negative 283.6 again because it's for 4. So negative 283.6 kilojoules per mole. And when I multiply those two, times, criminy, my bad. Oh, geez. Okay. No, that's not it. Oh, wait a minute here. Did I mess that number up? 4.3? Is that what it is here? Sorry. 543 moles here. Sorry. Which, of course, changes this here. Geez, I'm not having a very good day today. Is that better? 0.543? Let me just do that one more time here. I think I did the first one, I think. Okay, so 0.5433, and it goes on. Don't round that number, obviously. You need to keep that on your calculator. So it's, you know, the whole number's there. I'm going to take that and multiply it by my negative 283.6 number. And I will get, of course, here, delta H, the enthalpy change. Don't forget, it's negative 154. Well, that would be it. Negative 154 kilojoules, because once again, 3 significant digits in the question, 25.0. Okay? So negative 154 kilojoules would be your answer for that. Good? Questions, anyone? Yes, no? Questions, ask if you're not sure. Okay? You got to remember, when we're talking about molar enthalpy, we're focused on a particular reactant or a particular product, right? So, based on this reaction here, same reaction, of course, in this case here, we're going to get 4.50 megajoules. What's a megajoule? What is that equivalent to? Yep, 1,000 kilojoules. So we're going to get 4.50 megajoules, or we're going to change that to kilojoules, of heat produced. They want to know how much ammonia in grams. So you know me, I like this, right? And this is probably what you should have too. It keeps everything nice and neat, right? Lined up where you're supposed to have stuff. And basically what I'm saying here is, well, 4 moles gives me this. We know that. If I wanted to get 4,500 kilojoules of energy produced, 4.5 megajoules times 1,000 gives you the kilojoules, right? If I wanted to get 4,500 kilojoules, well, the first thing I guess you should ask yourself is how many moles is going to do that for me, right? Because if 4 gives me that, how many moles gives me that, right? And then we could use, we know that. We also could find the molar mass here, by the way, that's 17.04 grams per mole. And then we could figure out the mass that would be equivalent to, okay? So let's do that. Well, let's look at our little formula here, I guess. If you want to use this. If I wanted to make 4,500 kilojoules, if that's going to be my enthalpy change, okay, how many moles is going to do that for me? If, and once again, we're talking about ammonia specifically here, so 4 moles gives me 1134. The molar enthalpy of that is a negative 283.6 kilojoules per mole, right? So we're going to divide both sides by that, of course, right? Divide both sides by a negative 283.6, and we will get 15.867. And so on, and keep that number in your calculator. Notice I had negative enthalpy change, negative enthalpy, negative molar enthalpy. Those two cancel to give me positive moles. Make sure you're using the right units there. So I know that 15.867 moles, 4 gives me that, 15.86 gives me that. Okay, that's the relationship here. And once again, you could have used the ratio proportion, cross multiply and solve if you want to. Okay, so you can do that. Well, I know that this is 15 moles. I know the molar mass is 17.04 grams per mole from NH3, of course. Multiplying those two together, you will get a mass of 270 grams. Would be how much NH3 you'd have to use in this combustion reaction to get 4,500 kilojoules of energy produced, or 4.50 megajoules. Okay? Any questions on that one? Yes, no? All we're doing is adding a few more steps in here, right? Same stuff we did yesterday. We're just adding a few more things. Okay? Last one. I'm going to let you guys work on this one on your own here. So you guys go ahead and do record there for a second. You know, ask, we've got scheduled help today, and so on and so on. And like I said, we'll probably have a quiz tomorrow based on that. Tomorrow, I don't want you to worry about this. Well, I do want you to worry about this because it's homework. But you need to be, at this point, we should be able to do that part there, yeah? And in 3 different ways, of course. So that's what we'll do tomorrow. All this other stuff, we'll probably have a quiz on that on probably Friday would be probably a good day, or Thursday or Friday, we'll see, I don't know. But we'll give you back your other quiz right away here, okay? All right, I got some. Okay, so balanced chemical equation, of course, formation. This is what it should look like. This is what I would expect for tomorrow's quiz kind of thing. 2 calciums, 2 carbons, 3 oxygens, 2 calcium carbonates. You're going to look up the heat of formation, of course, during the formation of calcium carbonate. Look up the heat of formation. It's like 1207.6, negative 1207.6 kilojoules per mole. We are making 2 moles, of course, so we need to make sure we double that. So that is your balanced thermochemical equation there that you would expect to have. All right. Well, that's fine. We want to know what mass of calcium here would produce, not 2415, of course, but in this case here, 350 kilojoules of enthalpy change here. Produce 350 kilojoules instead. So we need to figure out the mass that's going to do that. Well, once again, line everything up here. Molar mass, 40.08, by the way, grams per mole. How many moles? We know, once again, that 2, right, balanced chemical equation, 2 gives me 2415.2. Well, how many moles is going to give me 350? So you can use your equation here, delta H equals N delta RH for this reaction. If I wanted to make 350 kilojoules here of enthalpy change, once again, we need to know the molar enthalpy. And for calcium, of course, because that's what we're focusing on here, the calcium only. For calcium, the molar enthalpy change, well, 2415.2 kilojoules for 2 moles of calcium, right? So once again, it comes out to that same number, negative 1207.6 kilojoules per mole would be the molar enthalpy of the calcium, which happens to be the same, of course, as the calcium carbonate there. Dividing these two sides here, 350. Let's see here. 350 divided by the 1207.2, or those numbers there, you're going to get about 0.289 moles. All right? So 0.289 moles is going to give me the 350 kilojoules. So I'm going to put that in here. Remember, do not round it. Obviously, I'm not going to write the entire number down, but don't round the entire thing. 0.289, we got N, we got the molar mass. We're going to multiply those two together, and we get 11.6 grams. All right? 11.6 grams of calcium will give us the 350 kilojoules of energy produced, exothermic reaction, of course, et cetera, et cetera. And that's what you want to have for that one there. So hopefully that's good. If there's any questions, let me know. But that's what we need to have for that. Once again, okay, the 2 here gives us the 2415.2. The 0.289 here gives us our 350, right? You can do ratio proportion if you wanted to. That's fine. Same thing, right? 2 is to 2415.2. Well, how much would give me 350? About 0.289. All right? So that should be good there. If there's any questions, let me know, and we can chat about that. All right?